So null hypothesis is our default assumption about population. It's something that we assume is correct, okay? Usually null hypothesis, you take a null hypothesis as no effect. Imagine that you would like to know if you eat one apple a day, will you get healthier? For example, your cholesterol level in blood will get smaller. Well, the null hypothesis will be that apples do not influence the cholesterol blood, right? So no effect. So most of the time when you take a null hypothesis, you use this rule, no effect, no difference, no change, okay? Sometimes it's quite difficult to take a null hypothesis. In this case, if you have any difficulties, take just the most probable situation, okay? We will discuss this a bit later. And then you always have alternative hypothesis, something that is opposite to the null hypothesis, right? So if you reject null hypothesis, you will have to take another hypothesis, accept another hypothesis, and it will be your alternative hypothesis. And the hypothesis test allows you to get a value and get a chance that your sample came from the population where the null hypothesis is true. If this chance is small, you reject it. If this chance is large, you accept it. And then if you reject null hypothesis, you accept alternative hypothesis and vice versa. So that's the basic idea behind the hypothesis testing. Now let's get back to the hypothesis testing on the average and discuss a little bit more. Well, first of all, if you compare average value of one sample, you have actually three possible null hypotheses. Either parameter of the population is equal to a certain, which we just discussed recently. But you can also make an assumption that, for example, your null hypothesis is at least, meaning equal or larger than the given, right? So it's not smaller than the given. Or its opposite, it does not exceed a given. For example, it's equal or smaller than the given, okay? For example, if we talk about contamination level, that will be a good hypothesis, right? So in this case, we assume that our contamination level, for example, does not exceed a certain one, okay? So in these two cases, you have to use only one tail to calculate a probability, either left tail or right tail. Let me show you again the examples. Okay, let's say we have the following null hypothesis. So it means that average height of all adults in the city is at least 175. So it means that we assume that average height of these people is pretty high, is pretty large, right? So what it means that every time you have a sample smaller than this one, it will be extreme sample. But if you have a sample larger than 175, it will not be extreme at all. So again, we have only one direction of extremeness here. Which one? For example, this sample, 174. 174 is smaller than 175, right? So it means that this sample will be quite extreme for this null hypothesis. But it's not pretty far, so the extremeness will be not very large, right? So every time you have a negative t-value will be extreme for this null hypothesis. And the more negative is it, the more extreme is it. So it means that the p-value should become smaller when the t-value become more and more negative, right? So it means that we have a left tail as a direction of extremeness. So in this case, every time you have a sample equal to 0 or 1 or 2 or 3, it will not be extreme at all. So in this case, the p-value should be large. But every time you have a sample with t-value going in this direction, your p-value should be smaller and smaller and smaller because the sample becomes more and more extreme. So the chance that your sample came from this population should be getting smaller, right? So in this case, we use a left tail to calculate a p-value. So if we calculate a p-value, in this case, it will be this area. And then you can see that this area will become small, for example, if you have minus 2.5 or minus 3 and so on, okay? So again, if we calculate it, we will get a p-value 0.31. So still 31.2% chance to get a sample as extreme as ours or even more extreme if our assumption about population is correct. So it's still a pretty good chance, so we cannot reject null hypothesis here. If we take the second example, now t-value is +1, so it means it's not extreme at all. So we can expect a p-value larger than 0.5. And you can see indeed the shaded area is larger than the half. So we can see that the p-value is 83.3% chance. So this sample is not extreme for our null hypothesis. Then finally, if we take the last case, we have -3. So this is the chance to get a sample as extreme as ours or even more extreme. And the chance is very small, so it will be less than 0.5%. So it's 0.45% chance chance to get a sample as extreme as ours, or even more extreme, if our assumption about the population is correct. And this chance is too small. So in this case, we should reject null hypothesis. Okay. Now let's consider another hypothesis. So in this case, we assume that average height of people in our city does not exceed 175. So it's 175 or smaller, right? So in this case, we have an opposite situation. Every time sample has average below 175, it's not extreme. But if sample has average above 175, it will be extreme. So in this case, positive t-values will be extreme. In this case, we have to use right tail to calculate a p-value. So once again, this is the first sample, that's the t-value. So now this is a sample as extreme as ours. And all these samples with all these t-values will be even more extreme. So that's the p-values. That's the chance to get a sample as extreme as ours, or even more extreme. And then you can see that it's about 68.8%. Okay, so not extreme. Okay. Then in this case we have 1. In this case it will be extreme, but still pretty big p-value. So you can see that it's about 16.7% chance to get a sample with t-value of 1 or larger, if in fact average height of all people in the city does not exceed 175. Okay. And then finally, the last cases, in this case it will not be extreme at all, because it's -3, and it exactly fits with our assumptions that the average height of people should be not larger than 175. We have 169, it's definitely not larger than 175. So in this case, you can see that the p-value will be 99.6%. Okay. So that's how it works. And now the question is, I used to say not extreme or extreme in this case, how to find out if you have to reject or accept null hypothesis. Well, that's the significance level that tells you that. You remember when you calculated confidence interval, you used a confidence level, right? So 95, 99% of the chance and so on. Significance level, it's the opposite thing. So it gives you the chance that is outside this most common cases. Okay, so if this chance is too small, if this chance is too outside this most common cases, then you have to reject null hypothesis. One of the most widely known value in statistics is 0.05, which gives you a 5% chance. So if you use the significance level 0.05, it means that every time you calculate confidence interval, you have to calculate 95% confidence interval, and then you have to compare p-value with 0.05 in order if you want to reject null hypothesis. This is pretty bad case, because many people do not understand that even if your p-value is small, you still have a chance that your assumption about the population will be wrong. We will discuss this in the next video, but so far, just remember one thing. You have to define your significance level and the corresponding confidence level before you start the experiment. That's important, because significance level and confidence level, it's a chance to get a sample. So it means that you have to define them before you get a sample, actually. And that's a very important thing. And then just an illustration, for example, if you use significance level 0.05, so every time you have a t-value in the green area, the hypothesis will be accepted. Every time you have a t-value, for example, in the red area, the hypothesis will be rejected. And here we are talking about the two-tail test. Of course, if you have right tail or left tail, it will be a bit different. And then the last thing I would like to remind you, it's again to remember that confidence level and significance level, it's not something that you can tune after your experiments is done. Confidence level and significance level is a chance to get a sample with a certain properties. So it means that you have to define your confidence and significance level before you get a sample, because afterwards you cannot tune them just to meet your requirements. That's important to remember.